Just someone say like.
This is our drop test recorded presentation. My name is Connor Ive.
My name is Bradley Bourgeois.
My name is Landon McLeod.
To start the project, we were first given a list of requirements from the customer. The two main ones were to create a repeatable drop test that was able to record data. This data would include acceleration, velocity, displacement, and force. There was also a few preferred additions, which was to keep the data noise to a minimum, ensure that the device was easy to use, also get acceleration, velocity, displacement, and force, and that we were able to collect a large quantity of data points. Using that, we created a list of functions and constraints, including for functions that it is repeatable, it is able to drop the phone, it uses Firefox to collect our data, and it tracks force, acceleration, distance, and velocity. For our constraints, we had it can't break, there's experimental safety, it's easy to use, limit our interference with the device, cost-effective materials, small intervals, and smooth curve. From there, we've made a list of our 3 most important functions for our device. We came up with phone safety because the phone was the main part that was getting dropped. We needed to protect it using a measuring device, and we needed good products to ensure that it wouldn't break when it landed. Then repeatability. It was the customer's request, and we also needed to ensure our results were consistent for each use. And lastly, it collects data, another customer request, and we needed to ensure that our drop test is functional. For our design process, we first drew inspiration from a lance mount drop tester. Oh, wait, it's already out. Yeah.
This machine, this is what's called a free-fall drop tester. And what this machine is used for is for dropping packages in various controlled orientations such that you can test them and concentrate impacts on specific, and demonstrate that right now. And what I'll do now is perform one on the top of the container, one on the short side of the container, and one on the largest side or face of the container.
We gotta go back. There it is. Use the mouse again. Here. Come on. They're right there.
The idea that we drew from that lance mount video was to use a pulley system. As you can see here, we would use the pulley system, we would pull it, and this would bring up our large platform, which could also ensure the repeatability side of the project. So we would pull it up, pulling the platform with the phone attached to it, and we would simply release it, letting this fall, bringing the phone down, and we would have Firefox open to record that data. As you can see here, this is kind of a sketch. These are the pulley systems, and this is our platform that would bring up and drop down. And this would be our phone landing pad to ensure the phone safety as well. Some pros that we noted was that the pulley would pull platform, so this would be easy repeatability. We would just pull it up and drop it. It'd be very simple. Some cons, as you can see, it was not very simple design. It'd probably be kind of hard to design in itself and build it. And then it wasn't very transportable. We'd have to deassemble the pulley system to ensure that it wouldn't break. And then human interference would also been massive because we couldn't ensure that it would fall at a constant rate without dropping or flipping. And then we came upon this video, which was I think that's a quick one.
It's pulled up already.
There.
So as you can see right here, it would ensure the repeatability of the design. We'd be able to just flip the flaps over, and then once we place the object, which in this case would be a phone, we'd simply be able to pull it out. pull it out and it would simply drop down. So it'd be easy to record our data. So this design, as was stated right here, it followed most of the design functions in our house equality and the constraints. It allowed for a smooth drop, which limited human interference. And it would be easy to design, just a retractable platform with a bottom platform on top and access to go through that. And it'd be very simple to use. All we have to do is pull it out and reset it after each use. So then we started designing this concept, just the base and the collapsible platform. Pros, it was very repeatable. All we'd have to do, as I said before, is just pull it out and put it back in. And then it was easy to set up and easy to take down. Being very portable would help. All we have to do is just carry the base whenever we would carry it around. Some cons, it might be complicated to build, and the fact that we would have to pull it out and it would be resettable without us affecting the actual collapsible platform. But ended up choosing it because it was most repeatable and the structure was most transportable. And then some more problems that we discovered with this design was to make it to where it would support the weight of an iPhone without collapsing. This would also enforce the idea of experimental safety and our measuring device safety. And then we tried to make the point of how can we make it repeatable without having to set it up in between each use. And then deciding on material for the base of our drop test, that would also be a big measure in the fact of the experimental device safety. And then how can we keep it from folding on the weight of the phone, as mentioned in this bullet point as well. And then how we solve these problems in our design. Instead of building the base out of wood, which was our original idea, we decided to use a foam block. This would be a strong base as well as it would support the weight of the phone and also help impact it. And then we use circular wooden spools as kind of a flipping dropping mechanism, so the pieces of the retractable platform would fall without any outside force, just the weight of gravity would pull them down. And then we cut into the foam block for each support beam. This would be easy for us because we could just hot glue each support beam in. And then finally, we used a lot of popsicle sticks to make the base and the support, just because they were strong and durable with the hot glue. This was our final design. As you can see, these are each of the support beams, and this is our retractable platform. So all we would have to do, as drawn in this CAD, we would simply have to pull out the retractable device, and the flaps would fall from the weight of the phone. The phone would just land in this area, and it would measure the data collected. And then this is our bill of materials. As you can see, the most expensive items were the phone block. We decided this was worth it because it would ensure our device safety, which was most important in recording repeatable data. And then the glue gun, it was also important because it would ensure that our base was very supportive.
Also, side note, I'd like to mention that our apparatus overall was relatively cheap, and the reason we chose this is because our target customer was a Novus user rather than some highly technical company that's using it for some industrial use. So.
And then this is the final design of our drop test. As you can see, we built it out of popsicle sticks with the foam board at the bottom. And then we had bubble wrap to ensure that our device would be safe. And then we added some extra rubber bands around each support beam just to ensure that they would stay together and they wouldn't separate under the weight of the phone.
It's the cube.
And then here is a real-time video of our drop test.
Very good.
Okay. And so here, these are some of the numbers that we exported from Firefox into Excel in order to demonstrate the data that we got. So right here, you can see in the orange is going to be our acceleration that we got versus time. We got about 195 data points from this, and from the acceleration, in theory the max acceleration or the acceleration of the fall is around 9.8 meters per second squared, because that's the constant acceleration of Earth's gravity. But here you can see this is where the atom impacted the ground, and there's a spike in acceleration, which you can also see here and here. And so this graph right here demonstrates the acceleration that we got versus time and below. And so the maximum acceleration upon the collision is 84 meters per second squared. And then here we have our velocity versus time, which we got from the kinematic equation. Velocity initial plus acceleration times time equals the instantaneous velocity. But the velocity initial is 0, as you can see here. And so since this right here was about the impact time, we took our this right here is our impact time. We took our peak velocity from around that area, which was 2.96 meters per second. Right here you can see is our force versus time, which is simply just the mass of our object times the acceleration, and then the maximum force that we got there is 12.2 newtons. And then here we have displacement versus time, which is basically the same thing for velocity. That velocity is for acceleration. It's the initial position plus the velocity times time, and it shows an increase in velocity, but this is the inverse of what our object does, because our object is falling. But the displacement, the magnitude of the displacement is accurate here. It's 0.49 meters, which is about half a meter. So those are the numbers there. And then here, as you can see, we have several different increments of data that we collected too. And then this is our overall hierarchy and just the steps of our design process. I don't want to go into too heavy detail here, but essentially, this is just a general overview of the process that we took to get to our final design, and these are the things that we highlighted. These here were the things that were important to us: the matching peak magnitudes, reducing the noise, the ease of training for a novice user, all that stuff. If there's anything you want to add to that?
I'd just like to note that we had a thing called repeated steps here. This is when our first two designs weren't attainable for whatever reason that we chose not to do them. So as you can see, we kind of had to go in circle a few times just to get our optimized product, which was our final idea.
Yeah, and all of this was based off the formula of the engineering design process that we followed. And then here's just all the things we have from our house of quality, basically how we compared the details of our constraints and our functional requirements, and how we measured this, whether our ability to meet these constraints and requirements were done well or successful or whatever, in order for us to accurately compare what's most important in our design process and which one of our alternatives would fit our goal the best. And so to conclude, we came up with these three biggest requirements: repeatability, phone safety, track data. Our phone was safe. The data, all the data, as you can see, that we wanted to get from the drop tests we got, and we were able to repeat this test several times.
Thank you.